So it's my great pleasure to introduce today's speaker. I'll be brief because we all know him very well. So, okay. Yanyan received his PhD at the Quran long time ago, and he joined Rutgers from 1990. And he has been a distinguished professor there from 2000. And he holds many guest positions, including the one at the Beijing Normal University. He received many honors, and among those are Simon's Fellow this year and the inaugural class of fellows from American Math Society. And he is on the editorial boards of many journals, including Advances in Math. As we all know, the Yanyan made tremendous contributions to advancement of the PDs, geometry and theory, analysis of PDs. Lately, he has been producing some breakthrough results on PDEs arising from mechanics, especially the theory of composite materials. Today, he will talk on this, which I'm eager to hear. Yanyan, all yours.
Thank you, Humbei, and thank you very much for the kind introduction. And it's a great pleasure for me to be here, to see you and to see many friends. And so I will share the screen now. So today I will talk about this gradient estimate for the insulated conductivity problem. I will explain what it is. So I will mention some earlier results, and then we'll be talking about a recent result with my student Zhuolun Yang on this problem. So first, I will restrict to mainly just the gradient estimate. So we know that for harmonic functions, if we are in the domain, and if we are given any control in low norms, for example, H1 norm, L2 norm, and then when we go to the interior, we will have higher derivative estimates. So for instance, the gradient estimates. And so in a bounded domain, and if we look at the divergence form elliptic equations of second order. So the coefficients is elliptic. So this matrix is symmetric and have a positive and lower bound and upper bound. And we give some regularity. Not only L infinity gives some continuity. For instance, gradient bounded. Then if we have H1 norm bounded by 1, when we go to interior, we will have a gradient estimate. So if the coefficients is not so smooth, so still in a domain, still elliptic, we have uniform ellipticity and second order divergence form equation, and give control of H1 bounded, then the de Giorgi-Nash theory will tell us that there is a Holder estimate. The Holder exponent depends on the ellipticity. So this alpha in general cannot reach 1. So we know that. So it will depend on this ellipticity. So there's one situation which comes from, at least coming from the study of composite material. So is like this. So we are in a domain. So this omega is the bigger one. So this is a unit size. It's like take a ball of radius 10, for example. And there are two inclusions. They are unit size. They are not very, very tiny. So they are unit size, boundary are smooth. And this is another one, boundary are smooth, unit size. But they can be getting close. So this is the epsilon is small. So the distance between them are small. So, in the limit situation, they can even touch. So the coefficients we are given are piecewise constant. So let's say inside here, we have a K, and here we have a K, and outside we have a 1. So the K is greater than 0 and less than infinity. So they are elliptic. So this is elliptic. And but the coefficients is L infinity. Coefficients are L infinity in general. So well, it's better than L infinity, but it's not. Yeah. So if you control, if you are given H1 control, now the question is, do we know that L infinity is under control? So the main point is this, the question is, you want this constant to be independent of epsilon. You want this constant to be independent of epsilon. So that's the question. So this does not follow from the de Giorgi-Nash theory, the general de Giorgi-Nash theory, because there one only get Holder, but there the coefficients are allowed to be in all L infinity coefficients. So here the discontinuity is rather special. It occurs across a smooth surface. So if allowing this epsilon depending on epsilon, allowing this constant depending on epsilon, so this result was known much earlier. So this is the rather classical, it's called transmission problem. So the transmission problem, will give you a constant which depends on epsilon. So for example, it is, I think this goes back to at least 1960s, at least, I think. There, this was well understood already. So the solutions were known, back then already known that the solution will be piecewise, in this case, will be piecewise smooth, actually, up to the boundary. And in here, piecewise smooth up to the boundary. And in the other ball, piecewise smooth up to the boundary. And across the normal, across here, the normal derivative has a jump. So then, so Ivo Babushka and collaborators, there were 2 papers, I think, and in 1999, quite some time ago. So in the paper they have is about, so the title of the paper is called Damage Analysis of Fiber Composites, Part 1, Statistical Analysis on Fiber Scale. So there, they used the Lemay system to make a model. So this is a homogeneous, isotropic, linear system of elasticity, which I will write down the equation. So they used this as a model, and they observed numerically that for linear system of elasticity, the L infinity norm of the gradient is actually independent of epsilon. So it's independent of epsilon. So, and my colleague, Michael Vogelius and Bonetier, they have a work on the first work on such situation to see whether one can prove this rigorously. So actually they were both former students of Ivo Babushka. And so they started with 2 dimension. In 2 dimension, if we take 2 unit ball and let it touch each other. So, and you take a unit size domain, you take a domain, okay. So then you take ellipticity K inside, K here. It's okay to take 3 different positive constants. So I just take simple one to take 1 here. So we are having a piecewise constant coefficients. And this is the equation. And assume that you have a H1 solution. And they prove that the gradient is L infinity. So namely, so the main thing is here. So the main thing is here. So L infinity. So mainly is here. So gradient U is L infinity. Because as we said, by the classical transmission problem, we know that away from this touching point, everything is fine. Everything is fine. So since the proof was using complex variable, because in 2 dimension, a harmonic function, so this will be harmonic here, a harmonic function, it can be linked to a holomorphic function, the real part of holomorphic function. So Michael told me this problem, yeah. So showed me the results, and well, actually at the time, so I was quite surprised to see this result, and so wondering, whether there's a PDE theory of it. So I've never seen such a result before. So so then Michael and I worked on that and have a PDE result. So namely, if we look at 2nd order divergence form elliptic equations in all dimensions with piecewise smooth coefficients, like the domain geometry are like what we described before, like this. So piecewise smooth coefficients up to the boundary piecewise smooth. And they are elliptic, diverse form. And in that case, indeed, gradient U is bounded, independent of the distance epsilon. And when they are touching, gradient U is in L infinity. And so that, because when we prove that, our starting point actually is de Giorgi-Nash. So it did uses the elliptic equation. So it didn't one need for linear system of elasticity like Lemay system. So one needs to do differently. So then with Louis Nirenberg, so we proved such a result for divergence form elliptic systems with piecewise smooth coefficients, so which include linear system of elasticity. So about linear system of elasticity, so it is such equation. So the number of unknowns is x1 through xn, and the number of equations is u1 and un. So the number of equations and the number of unknowns are the same. So here is a n by is a So here running through n by n, and this is running through n by n. So we have n unknowns, n equations. So this corresponds to n equations, n equations, n equations, n unknowns. So, so the ellipticity is given by Aij alpha beta. You test against symmetric matrices. So we have positivity. So that is called a linear system of elasticity, yeah, the elliptic one. So for system, there's one type which is stronger. It's called strongly uniformly elliptic. So which is tested for all matrices. And here you don't impose this symmetry. The symmetry is, you see that you switch Ij alpha beta, you see Ij and alpha beta, it's the same. Yeah. And here you can switch I and alpha. So this corresponds to the invariance when you set up the problem, model the problem, one has translation invariance and rotation invariance. So this invariance will give your equation some invariance. So the Lemay system is an important case, and so it is like this. This is you still have n, you have n variable. This is Laplacian u as a vector. So you do divergence and take gradient, and ellipticity is, this is positive, n lambda, n is the dimension, and this is ellipticity. So when we try to prove some results, we first look at the equation case, like a conductivity case. So that's a scalar equation. And when we go to system, and we certainly want to look at this system first, like in Babushka's. I use this first. Okay. So let's go back to the conductivity problem first, the scalar equation. So we come back to the geometry. So we have a domain, which is a smooth, nice one, unit size. And D1 is a domain, D2 is a domain, unit size. And epsilon is the distance. So here, the epsilon will be small. So epsilon positive will be small. So you are interested in obtaining estimates, either epsilon independent or pin down the dependence on epsilon well. So so let's, for simplicities, from now on, let's just look at D1, D2. For simplicity, let's just think of them as strictly convex. So things can be done for more general, for some results, but let's just take it for simplest case. So then this is the setup. We have K inside ellipticity, K here, and the 1. So it's a transmission problem, and we are interested in the quantitative control of the gradient, mainly, say, in terms of epsilon and K, for instance, because when K goes to infinity, ellipticity deteriorates, and also when K goes to 0, ellipticity deteriorates. So, well, for the equation, the maximum principle immediately gives epsilon independent L infinity norm, and gradient, as we mentioned, gradient L infinity is bounded by a constant depending on K. So one asks naturally, say, what happens for K goes to infinity, and in particular for K equal to infinity, or for K goes to 0, and in particular for K equal to 0. So for the conductivity, this is the perfect conductor case. This is insulated conductor case. So for K go equal to infinity. So for K equal to infinity, and here actually the results here stated does require strictly convex. Otherwise the rate will be different, but one can also capture the rate. So let's first start from K equal to infinity. So for K equal to infinity, so inside we have infinity, A infinity is infinity, inside two balls, one outside. So one, infinity, infinity. So of course, this does not make much sense, it looks like, but you can define it in the following way. You take a K and put a boundary condition like this, you solve it uniquely, and you send K to infinity, and this UK will goes to U. So uniquely. So you can take it as definition. Or you can define it by inside a constant, inside here some constant. The two constants are determined by two non-local boundary conditions. The normal integrating on here, the flux, you integrate it, it should be 0. So these two conditions pin down uniquely the two constants inside. So that's the solution. So two equivalent definitions. There are some, these are more from engineering direction. One of them is a book, perhaps this one. I think this one is a book, and this one is a paper. So there they produced special solution. In the case n equal to 2, they produce solution that the rate is like this. When epsilon goes to 0, the gradient U will be like this. So then, the first work is by Amari, Kang, and Lim. So they look at the in R2 and a global situation, and they pin down that the rate in this both, I think. So they pin down the rate is exactly that. Yeah. So then one eventually the result is in go to all dimensions and can be localized. And this is Alan. So the result is in 2 dimensions, it is that, and this is epsilon log epsilon in 3 dimensions, and in 4 dimensions and up, it is 1 over epsilon. So the rate is getting worse here. So, and this is actually optimal in the sense that you are able to find boundary value phi so that you actually reach this rate. So these rates are known now to be optimal. Well, it is also, let's, for linear system of elasticity. So this is the system, as we said, yeah. So as we said, if we take 3 elliptic constants, so finite case, so like 3 sets of numbers. So inside D1, you have 1 set of mu and lambda Lemay constants. Inside D2, you have a second set of Lemay constants. Outside the 2, you have the third set. So then you know that gradient U are bounded depending on the ellipticity. So this was known. And for the infinity, so if you if we make them to infinity inside, so one can also define it by taking mu and n lambda plus 2 mu, you have a unique solution. And then you send this ellipticity go to infinity, it will pin down one's unique solution. So in that case, if we look at the Lemay system, and so it was proved, this Jiguang Bao and Haigang Li, and so the rates are similar, are the same as in the for the conductivity scalar case. Still n equal to 2 is this rate. Yeah. So how about the for k goes to infinity and for k goes to 0? So in that case, so if k goes to infinity, for k goes to infinity, and in dimension 2, well, the right rate is actually here. So C is independent of K and epsilon, of course. So I think here should be this. So, okay. So I think it's 1 okay. So yeah, so that certainly should be square epsilon. So, and so this was first identified by American, Lim, and American, Li, and Lim in a two-dimensional case in a R2 and minus 2 Bohrs. This was identified, and they could. So the proof is much more than that. So they can pin down much more, different radius and so on, different K1, K2, and so on. So then proof also localized and proof with general domain in 2 dimension was made by Hongjie Dong and Haigang Li. And sorry. And so this 2D, this was settled. So for n equal greater or equal than 3, this is still not known. So what should be the right rate? And when we have both epsilon and k, so that's not known. For example, if we keep k equal to positive constants, we see that this rate, the gradient is bounded because this will take over. Yeah, so it's bounded. If we take k equal to infinity, this term is not there. So epsilon, we see gradient epsilon square root rate. So in general, when we had results earlier for k for fixed constant and for k equal to infinity, it is desirable to have a uniform rate with both epsilon k dependence, so that like this. Yeah, but that's not known yet, and it's certainly interesting to pursue. So for k equal to 0, this is an insulated case. So for n equal to 2, so in R2, so we take a harmonic function, fix any harmonic function, and at infinity, we assume they have the same ux goes to h. Then in that case, it was proved by, in the same paper, by these authors, and the same paper mentioned earlier, and we have this rate. So actually this problem, in this case, is dual to the k equal to infinity case. It's a dual problem. So therefore they have the same, so in 2 dimensions, it's a dual. So for k equal to 0, and for insulated case, so for n greater or equal than 2, so yes, so this is 0, k equal to 0. So you have 0, 0, 1. So this case, So a rate was given. So in this paper, so the rate was given. N equal to 2 is sharp, and I said here this is sharp. So, but n for a while, it is not known whether n greater or equal than 3 is sharp. So this is for k goes to 0. So for k goes to 0, so this rate is like this. So this is dual actually. And so here, and this is C over that. So, and this is proved by, but this is in the mentioned earlier that those papers, they treated both k goes to infinity and k goes to 0. And this is a sharp rate. So for k equal to 0, and insulated case for n greater or equal than 3 is that sharp. So this is the wrong date, so this should be 0. So then, so this has not been known for a while. And in 2016, Yun examined a situation in R3. So in R3, we take two balls and epsilon apart, and we take 0, 0 inside. Therefore, what one has is a Neumann condition outside on the boundary. This is on the boundary. And Laplacian U equal to 0 outside, exterior domain harmonic function. And at infinity, the U approach and Y are close together. Y is a harmonic function. So they are close together. And in that case, Yun showed both sides, the rate is not C over root epsilon. The rate is actually this number. So the rate is 2 minus root 2 divided by 2. So yeah. So this number is less than 1/2. So it's better. It doesn't. It's not as bad as square root. So recently, Zhuolun Yang, he's my current student, and so we proved that in n greater or equal than 3, indeed the problem, the estimate is not optimal. So this estimate can actually be improved. So the improvement is by a number beta depending on the dimension and the domain. So one can improve a beta. This result works not only for Laplacian, we can have piecewise, we can have second order divergence form elliptic equations here with smooth coefficients up to the boundary. So it's still like this. So one can improve. But our proof, as I will show, does not give a good bound. For example, it's not like this. For example, in this case, we are not able to say it is this bound, or so our bound is not as good. Yeah. So we can write down a bound. It's not the method will give an explicit bound, but that bound is certainly far from optimal. Okay, so I'll say about a proof. So let's just take a simpler, everywhere I will keep simplifying things. So let's say we take a setup. This is a dividing surface. So the blue one are enlarged picture of these two. So what I draw is here, the blue one here and blue one here. And we have some epsilon distance. So we just enlarge there, so to draw it bigger. And so this part is epsilon. So this part is like epsilon. And we just take, say, a paraboloid, and this is minus paraboloid. So we take any point here. We are going to make an estimate for gradient there. So we are going to estimate the gradient there. So we will prove this. There's a beta. So in fact, we prove the estimates give this. This is the more natural quantity. So this is smaller than this epsilon plus. So when we go out, this number will become a better, which is natural. So let's take a point. We take a point here. So this height will be proportional. We take this height, basically it's like this height, more or less like this height, proportional to, yeah, proportional to that. Yeah, proportional to that. So this is proportional to that. So we take this height. So we are in the following, we are going to take a gamma. So we are going to work with a small gamma. So this gamma, the choice of the gamma will enter into this beta value also. Yeah. So we are going to take a smaller gamma. And we are going to work, in order to estimate this point, we are going to work with a like a cylinder type domain, like this. Yeah, like this region. We are going to work inside that, a shape like that. And the R, we are going to take R is some with the right scale. So we work with this R. So then we prove a Harnack. So without loss of generality, we assume U is between 0 and 1. So it's positive. So we can, yeah. So this is the shape. So this is the shape 2R. So the shape is 2R. It's this shape. It's this shape with, so this length, this radius is like an R, yeah, 2R. And then minus of R over 4. So it's like a annulus ring type shape. So on that shape, if you assume the top has a normal derivative equal to 0, so one have Harnack, one have this Harnack. Well, the way I say, okay, yeah, yes, Harnack, yeah. So we have this Harnack. So this constant depends on epsilon, independent of epsilon R and U. So this C goes into that gain of beta. So yeah. So that's why our beta is not so so good. So not optimal, not optimal. Yeah. So for simplicity, let's simply take this x0 to be at the center. Okay. To be at the center. So take this. So this delta should be the square root of epsilon. Yeah. So then the shape here, so we have once we have this Harnack, maximum principle will tell us that the soup will be bounded by inf for the whole thing, for the whole, not only this shell, I mean, for the whole thing, you have Hanach. So once you have this Hanach, for the whole thing, oscillation will decay. We will get a beta prime, gamma prime, beta prime. So this number also goes into the gain. Yeah. So without any work, this oscillation is bounded by a constant. So with that, we are going, one obtained a square, 1 over square root. So by working with the domain with epsilon height and square root epsilon radius. So it's kind of flat region. In that region, so all the transformations are not singular, so it works well. So here, if we want to gain, we need to go out larger, so to get control. So once we have this, we are getting the control what we want. So we can make a transformation and flatten that part. So we can take a region like this is epsilon, and we can take a region to be root epsilon, should be okay. So we take root epsilon, and this is kind of fat like that, and then we can transform to here. So it will become such equations. So the bottom is a unit size, because you see this ratio is root epsilon. So this height is root epsilon. So it's a unit disk, and the height is root epsilon. And then on this here, we have normal derivative equal to 0, and we have an elliptic equation of divergence form, and this Aij is good, is actually holder. When you make this transformation in this scale, you can keep Aij holder. So in this situation, then one has estimates like this. So we are able to control. So for example, in our case, we can take this as 0 actually. So I think in this case, then we don't even have this part. So we can take as 0. So therefore, we can control the gradient like this. Or we can take here, if we normalize properly between, yeah. So yeah, we will see this. We are going, so when we normalize, we can normalize property. We can take a gradient estimates. You can always insert a constant. So we are going to see at the top, we see this L infinity, this. So we gain, So here we will gain epsilon to some beta to the whole thing. So when we scale back, when we scale back, so we have another root epsilon, and we get our result. So this estimate is by some results in our earlier work with Vogelius and Nuremberg. So we are able to obtain such estimates. So that gives the proof here. So that's just the beginning somehow step. And so for instance, natural question is whether or not one can obtain some result, like for example, in this case, is it possible to actually get this rate, or to look at linear system of elasticity, can one get such rate? So for linear system of elasticity, we do not know such result. Yeah. So because we have used maximum principle. For linear system of elasticity, it was not the same method as before. For the equation case, earlier we can get something like this. So we can get a gradient UL infinity will be controlled by something like root epsilon and say UL infinity. So this one can obtain. And one question is whether or not one can gain this bound, gain this beta power, and we haven't seen that yet. So we are trying to replace this Harnack part. So we replace this part. So we have not succeeded yet. And so I think I will stop here.
Okay, thank you for a wonderful lecture and congratulations on good results. So you improved the estimates to 1 over square root epsilon in 3 dimensions, right? Yeah. So let's take a few questions. Anybody have a question?
I do.
Yeah, please go ahead.
Hi, Yanyan, beautiful talk. Thank you, as always.
Oh, thank you.
So I was wondering, in that part where you use Harnack inequality, so instead of using Harnack inequality, you were able to prove a Hilder estimate, a sharp Hilder estimate, like solutions are Hilder continuous with some exponent alpha, which could be sharp, that respect the jump. Would you be able to improve this beta?
So to improve the beta. So to have a better beta?
Exactly, yes. I mean, of course, depending on how sharp your alpha exponent for the Hilder continuity would be inside of these. So replacing the Harnack by a sharper Hilder estimate on solutions.
On solution. So yes, that's where the beta, yeah. So it will be good to have different ways of doing it to improve the beta. So the beta, if we write down a beta like this, so it's not so good. So our way of proof. So even though I only describe this 3 dimension, but actually our results will go with any dimension n greater or equal than 3. And then the question is why the method doesn't work in 2D, for example. Okay, so that's exactly in 2D, we are going to see shape, they are disconnected. So that's the only place in some sense. So the 2D will be like this, 2 pieces. So our proof works for dimension n greater or equal than 3 because the shape will be connected. So the Harnack go that way. Otherwise, it becomes disconnected. And so because in 2D, we are not supposed to improve that. That's sharp. So that's where the 2D makes a difference.
I see. Another quick question. I understand that all those problems involve divergence form equations for physical reasons, but have people look at the non-divergence theory?
So for the earlier one, I think Jinggang Xiong had a paper. So the first, like for the earlier one, I think, a very good question, yeah. Yes. I know Jinggang Xiong has a paper for like my joint work with Borgelius. So one can look at uniformly elliptic case, and there are nitro numbers one should look, not nitro derivative order one should look at. And that was studied by Jinggang Xiong in a paper. I forgot the year. So it's a non-divergence. So I think it's around so around here. So it's a non-divergence. equation, 金刚群. So I forgot the year. So year, I forgot.
Okay.
Yeah. So that has been, there's a paper. So for system, I don't know. So I do not know whether there's a system one. That I don't know.
Okay. Okay, excellent. Thank you again, Yanyan.
Yeah. Thank you, Eduardo. And yeah.
Any other question or comments or whatever? So let me ask you this: your beta depends on the shape of inclusions, and what can you tell us? It's implicit, so it's maybe quite difficult to clarify. But can you tell us a little bit more about how it depends on what kind of geometry it depends on?
That's the one we are hoping to be able to do that. We are hoping to get that. So you see, our beta comes from mainly comes from this Harnack.
That's one. Yeah, Harnack. Yeah.
Yeah. So we are going to have a region like this, okay, for appropriate geometry here.
Yes.
And in there, we are going to have a Harnack. So that Harnack will be, so this Harnack certainly depending on this shape, So we have a Harnack, but that Harnack, to get Harnack to the usual method to get Harnack, it's usually quite far from optimal. And also not only that, you see, to go down, we are going to use this Harnack. Once you have this Harnack, so we are going like a dyadic down to get a holder control. So that's also not so good. That's also far from optimal. Yeah.
I see. So there is some other problems to look into. I mean, to reinvestigate this Harnack inequality and things like that. Right?
Yes.
That's
yes.
Interesting. Yeah. Very good. Yes. Yes. I couldn't hear you. Okay. Yes. Let's wrap up. And thank you very much for wonderful talk. And good to see you again.
Thank you very much. Good to see you, Hongbei. Yeah.
Yeah. Yes. I'll see you next week again. Okay. Bye, everybody. Thanks a lot.
Thank you very much, everybody.
Thank you very much. Thank you for all the participants, for your patience. Thanks a lot. And
thanks a lot for the talk.
Glad to see many friends. Yeah.
Thanks a lot, everybody.
Bye-bye.
Bye.
Thank you very much. Bye-bye.